Yeah, thank you very much, everyone, to be here. So I'm so happy to be back in Montreal after so many years. Also seeing so many familiar faces. Thank you for the people also joining us online. Um, yeah, so let's focus on this resonance enhancement technique. So I will actually speak twice today. So one before and one after the coffee break, but one that is more like this presentation for the next 30 minutes. And then I will try to be as concrete as possible with the lab one connected to instrument as you see here. And so for the talk for now, so I will really start from noise consideration, so the need for resonance enhancement, and some way to play with resonance. So for instance, with the Q factor. And yeah, so basically to showing all what we can do going to a higher frequency. And after the coffee break, then I will try, as I said, to illustrate this, even trying to lock PLL and for dissipation measurement on not a native resonator, but of Q control resonator. So yeah, so let's start with some noise consideration. Yeah, so we all know that lock-in amplifier excels at rejecting noise, but yeah, it's always good to define it. So the lock-in output, whether it is a phase or amplitude, is a stream of a lot of data. And so if you can make some histogram of this data distribution, then you end up with some histogram. And the histogram is supposed to be Gaussian. That means you have white noise. And so from this, we can extract basically some mean value, so that the one where you have the highest probability of finding the value, which is at the maximum. And then you have some distribution, which is called the standard deviation. So the SNR is simply defined as the standard deviation over the mean value, or yeah. And then, so you can, in this way, compare very quantitatively to SNR. Yeah. So here it's in dB, because most of the time SNR can go over many different range, and sometimes it's nice to have some log scale. So in this case, lock-in amplifier typically, so the one like the MFLI has 120 dB dynamic reserve. So if you plug 120 dB here, you divide by 20, that gives you 6. So that means that you can have 6 decades of SNR just from the lock-in measurement. If you now take the exponential of this, so 10 to the power 6, so that's 1 million. So basically, one lock-in amplifier can measure one part of signal in 1 million part of noise. And so that's what makes it very powerful. But that's not that's not the end of the story. So it's also important to optimize it. So basically to understand what are the parameters that are most critical. And so since it relies on modulation technique, so it's a coherent measurement. So you need to introduce some modulation. So modulation can be mechanical, electrical, optical, you name it, magnetic. And then you want to be in a region that is outside of, let's say, pink noise, 1/f noise, short noise. I mean, depending on the origin of the noise, but you want to be in the white noise. And if you just want to illustrate by looking at different, let's say, frequency here. So if I look at the blue here, then I see that at DC, this is where I have the highest noise, which is of course not surprising. And then if I move a little bit away, then it's getting a little better, but still not perfect. And then whether in this particular case I'm sitting at 5 kilohertz or 100 kilohertz, it's almost the same, because that means that I'm going outside some region of high noise density. But yeah, as I said, so why do we need good SNR? And that's particularly relevant for nanotechnology and all these things. Because when we shrink the size of the device, like nano objects, single atom, and so on, then of course the signal gets weaker and weaker. But on the same side, if you improve the signal to noise ratio, that means you can also go faster. So you can use it in both ways. But you know, if we really look at signal in real life, and actually this was a measurement done together with our friends in Basel. So you see that here you have actually even 6 decades. So that means that even if you use the best lock-in amplifier, and that you have basically 6 decades of that you don't use a resonator, that means that you're going to be in this region. So even with the help of a lock-in, is not going to be enough, and that's why you need resonator enhancement. At the same time, it's nice to look at this is an FFT of the demodulated output. So that's not just the values that you get from a sweep. So it's really so before I was showing the SNR with the Gaussian distribution that was basically just data as a function of time. And now if you take this data and make an FFT of it, this is what you get. And you get it for a certain bandwidth. So that means that you can also look at how the signal behave with respect to some other resonance. So especially if you're doing some multi-frequency. Of course, now this is all nice because the resonance is steady. But when you go to often you can have drift, you can have many things that will perturb this resonance. And of course, because the lock-in is measuring at a fixed frequency. So if you're looking at this fixed frequency here, so sometimes you will have some nice measurement, but sometimes you will have nothing. And so that's why you need to track it. And that can be sometimes very large. Maybe just as an example for the super high frequencies that Jorge mentioned, so you can also have it at the gigahertz. So that was for scanning nonlinear dielectrics, but there could be many applications for higher frequency too. And so now the challenge is indeed to track this resonance well from kilohertz, megahertz, or gigahertz. And so normally when you talk about resonance, the first idea that comes to mind is a nice Lorentzian. And so that's what determines so-called open loop transfer function. So basically how the system behaves in open loop. So before you close the loop, when you just see how it spontaneously changes. So one typical parameter, of course, it's the frequency, resonance frequency, but it's also the full width that have maximum, so the delta F. So that corresponds to the measurement bandwidth that is available for this with this sensor. So when you do such a sweep, so you can extract the gain, the Q factor, and so on. But the idea, so the reason why we do this is because you want to be able to fit some good models so that we can optimize the PI value in closed loop. And so we need to extract basically a transfer function. So if you know nothing about your system, a transfer function, the easiest way to look at it is basically the ratio between output to input. So you know how much you drive, you know how much you measure, and basically the ratio is going to give you a gain. But in real life, so normally you always have some cutoff frequency. So at some point there will be some value where basically instead of being steady, you will drop. So it's a bit like a low pass filter. And because we can characterize it and we know a little bit more, then we can also plug directly the value that is related to the Q factor. So that's how we can characterize the system. But now if you would like to close the loop on such a resonator, it would be difficult. So of course you want to sit here. But it's very difficult because the slope can change if we go on the left-hand side or on the right-hand side. Ideally, you would just want to control in up and down, and to, of course, be much away from the detection limit here. So the way to prevent, so that, and also that's why in tapping mode, for instance, you can people actually go more into this area because it's not possible to close the loop on the amplitude right away. So on the other hand, the phase, it's much better behaved because you can actually fit a nice linear slope here. And that's exactly what a PID wants. A PID wants to have a linear response. And that you can do directly at the inflection point. You can extract as well the Q factor, exactly in the same way as the F over delta F, except here you get it from the slope, so the dF over d phi over dF. And so from this information, so you can now basically sit here. So you could actually even remove this curve, this phase. The PID doesn't care about it. The only thing that the PID cares is basically the slope here. And now you understand why you need the PLL before you can close the amplitude, because you first need to track in this direction before you can track in this direction up and down. And that's why a PLL closed loop bandwidth always has to be faster than an automatic gain controller. So if I put everything together, so this is, of course, what non-contact AFM is all about. So you have a fixed frequency, as we said, we start. And so from this fixed frequency, we of course extract amplitude and phase. This is exactly what a lock-in does. And it does it orthogonally because it's always a measure in phase and in quadrature. And then you have first a loop here that you can close, which is going to be faster. So basically, you're just going to compare the phase to the set point and then adjust these frequencies that is going to be here. But while you adjust this frequency, you're also going to give it for the amplitude. And now this one, you know that you are going to be here because this one has already adjusted so that you are on top. And now you can close this loop, which we're going to be slower because you want this one to be faster first. And then when you combine them together, then you have everything. So the amplitude control and the phase control of this argument, which of course you can output there. So the nice thing here is that you can benefit from high Q. So you are quantitative because the amplitude remains constant all the time. And then your closed loop transfer function is also well known. But there is still a challenge with IQ resonator, is that of course, even with a PLL, when it's very high, it's very difficult to lock properly, especially when you go with Q that is above 50,000, or when you're at low temperature, of course, and in vacuum and so on. But of course, you also want to have the Q as high as possible because that means that your sensitivity is also higher, right? So, but when you get there, then you have a very long settling time. So basically, everything that I've shown you, if you want to do this very point by point, it will take you very long time because just a sweep, unless you know exactly what it's going to be, is going to take, you need to make a lot of sweep to get a lot of points because your bandwidth is just going to be sometimes even millihertz. And so that's why there is a different way. So there are two ways, basically. So either to use a PID set point sweep, and that was discussed already with Hans Hoek. He's not going to talk about it, so that's why I'm doing it now. And then there is a Q control method, which is also well known for a while, but then we can really explain it better in the context of high Q and open loop transfer function. So if we, so before you were used to basically sweep the frequency, see your resonance, do a nice fit of the Lorentzian of the phase, extract all the parameters. As I said, this can take even hours if you want to do it very accurately. But if you do some educated guess, so basically if you can close the loop even if it's not perfect, then you can easily do a PID set point sweep. So the PID set point sweep for a PLA is basically just a phase resonance sweep. So now the axis X is not frequency, is phase, and the X-axis can be amplitude or frequency typically. And now you can also extract very accurately the Q factor. So you can get the df over d phi. So not d phi over df, but the df over d phi. And that gives you Q with a high accuracy. So that's actually also very linear. And then you know exactly where you are at the maximum of the amplitude. And that gives you a very high confidence for the resonant phase. And by the way, so this sweep just takes seconds, even if you have a very high Q, because the loop is closed. So and of course, if you don't want to make a full sweep, you can also just look in the sweeper, change a little bit the phase set point of the PLL and see how it behaves, and you want to maximize the amplitude. So that's a very efficient way to optimize PLL and resonator with high Q. But otherwise, there is one where we can dwell a little bit more time. It's this Q control method. Actually, when I first encountered Q control, I did not understand anything at all. And but it's actually not so complicated because everything has a single frequency. So before we were talking about open loop transfer function. So when you sweep your frequency and you look at your resonance, then you have, as I said, an open loop transfer function. So that's what would be your native resonance. So at a fixed frequency, this is not, so the resonance is not going to change the frequency. It's only going to change the amplitude and phase. So that means that whatever wave you're sending to your resonator is just going to be detuned and basically amplify, which is what you want. And normally you output this and now you start to play. You measure, you get your images, you do your PLL, whatever. But here what you can do is that you can actually rectify it. And by rectifying means that instead of having a native open loop response, you want to have an engineered open loop response. So before even you close it. And so for this, you basically now create a new wave that will restore with a certain phase shift and a certain gain. So that what used to be with a certain Q here is going to have a different Q. So basically, and of course also the amplitude response. So now your effective bandwidth is going to be modified by this Q here. So that's very useful if you want to damp it in order to go faster, or if you want to boost it in order to have higher sensitivity. So for in lab one, this is a little bit more complex because you're always using lock-in. So lock-in is, of course, again, measuring amplitude and phase. And with this, we are sending basically the 0 and 90 degrees wave. So both of them. And then we just have a P. So we're not using a PID, we're just using a P, which is just proportional. And then we combine them. And of course, if you combine two sine waves that are the same frequency, but that have different amplitude or phase, this will also make a detuning. And so that's how you generate this new wave, and then you can close the loop. And of course, this is done, as I said, at a fixed frequency, and nothing prevents you from then basically now continuing the job with the PLL while this loop is running for the resonator change here, and then have a PLL with a high Q. So now I will show you this after the break, how it works and how this also changes SNR. So basically, and so this you will see live, but maybe just as a teaser. So that's how it looks like in lab one. So you need these two lines, or two demodulators that was in the graph before. So basically, these two lines here, X and Y. And so we combine with PID these two waves so that it's perfectly match the type of shape you want on the output. And so in this way, you have a Q that is either boosted or damped. Yeah, and so so this was all done at, as we said, as a single frequency. But the nice thing is that with the same box, you can also extend that to multiple eigenmode, multiple harmonic, and so on. And so before I pass the mic to the speaker for today, I would like to show you just 3 examples. So one of them, it's basically well known. It's a bimodal, but actually could be multimodal. And no one limits you to 2 eigenmodes. I think this started with Ricardo Garcia, Santiago Solares, and many afterwards. One of the first time when I heard it was also in Basel when they were doing basically 2 amplitudes. So one that is, the first eigenmode, and then the second eigenmode, which is a small amplitude and lower Q factor. And when you do this, you can use it one with a large amplitude for stability, one for small amplitude for short range forces. So that's very convenient to use these 2 eigenmode. But otherwise, you can of course use it one for mechanical, one for magnetic, one for optics, one for electrical. So that gives you a lot of more flexibility. And of course, the idea is that you can do that in single pass. Yeah, so that for the standard, let's say, bimodal one. Then there is one that is for dual frequency resonance tracking. So this is, of course, a bit less common in NCFM. So instead of having just a free end, you just basically have a clamp end. So basically, when you are in contact, so it's called a contact resonance. And so from this, you will have, this is more, you have a much more frequency swing. Sometimes if you do it for piezo response force microscopy, you have a phase flip, so you cannot use the PLA because the slope of the PID changes, so you cannot use the PLA. And so in this way, you use an amplitude modulated technique. So you basically measure psi bands a little bit below, a little bit higher above the resonance. You make the difference of this. So the difference look actually like fairly linear in between these two. So that actually gives you a slope. And of course, the slope is 0 when you're at the resonance. And once you do this for 1, so no one prevents you from doing for 2 or even more if you want to. And that's very convenient because you can do, for instance, so basically the resonance that is in this direction, but also the torsional one simultaneously. And that's just simultaneous. And then one last example, which is a bit more recent, and I like it very much. I'm promoting it to to many customers now. It is a heterodyne FM KPFM that was actually started in Japan. And it's a very smart technique because for a long time people were using this FM mode where you basically have sidebands that are plus minus the resonance. So typically within this resonance, so you can have some AC electrostatic modulation. So you have a DC, an omega, and a 2 omega. But usually it's at low frequency, 400 hertz, maybe 1 kilohertz, depending on your Q factor. And but that's very crowded. So that means that it's a little, the bandwidth is limited. It's easier to have sometimes crosstalk, but also if you modulate faster, then you will quickly go out of the resonance, and therefore your signal is going to be attenuated. So it makes it very, very difficult in terms of SNR as well. So basically, instead of doing F0 plus minus FM, so a small modulation, use the FM, so the modulation frequency, equal to F1 minus F0. And now if you do F0 plus FM, so it's basically F1. So that means that in this way, and of course this is phase coherent. So that means that it's still an FM technique because you are sensitive to the phase, not to the amplitude. And you send that directly to the amplitude of the second eigenmode. And of course, you are exactly again at the maximum amplification factor because you don't want to be sitting here or here. You want to be sitting at the maximum. So you have a good of course, the Q factor is a bit lower, the stiffness is a bit higher, but still you have a good measurement, and it's still a phase sensitive technique. And all of this, everything that I've shown you, of course, now the tutorial in the afternoon, I cannot show you all the details. It will probably take hours. I will try to show you some good highlights in the next half hour after the coffee break. And of course, we are here for the rest of the week. So I think it will be great to continue the discussion during the NCFM. So with this, I'm jumping to conclusion. So I was... So starting from SNR consideration, of course, we love lock-in amplifier, but it's not the end of the story. You also need to have resonance enhancement, so you need to boost your signal because the lock-in is not going to touch the signal. It's only going to reduce the noise. So you need both, especially when you are measuring weaker and weaker signal. But if you do that, usually you also have to be smart about, tracking the frequency and all these things. And then you can, on top of it, do some so-called resonance engineering by having engineering the right open loop response so that your closed loop response is what you want. And then once you've done this, then no one prevents you from doing it at higher frequency.